All right, so in 1.2, the main objective is to look at a scenario and try to come up with a differential equation that models what's going on. Okay, so with a good model, you're going to have two things. One, you want to make sure you identify the variables that change the system. And you're also going to have a set of reasonable assumptions. Okay, now oftentimes you're going to get a differential equation, and then this differential equation for physical situations usually time will be involved. Okay, so therefore the solution, which again we're not going to solve them yet, but the solution describes the system in the past, present, and the future.
Why do you write Z? Like, I know what it stands for, but why are you?
What did I write? What? So we're going to get differential equations for all these models, and typically this differential equation will involve time as a parameter. And then that means, because time is a parameter, that we could investigate what happened before or what's going to happen in the future. That's basically what we need to know. So we'll run through a few scenarios, some of which you've probably seen before, maybe one or two that are kind of new, but most of the new stuff will be in the homework, and your job will just be to read. Sometimes all you're going to do is translate. It's not too hard. You just have to figure out where the derivative comes into play. So let's start with this example. Let's say you have a free-falling body. Let's say you have a bowling ball, and it's tossed upward. Looks like a sad bowling ball. What's what?
Identifies the variables.
That changed the system. Sorry. Okay. So now, reasonable assumptions. Initial height. If we have some upward motion, that means that there's an initial velocity as well. Mm-hmm. So with the initial height, initial velocity, what's the only thing that's going to affect, once this thing's in motion, the position? Yes. So another assumption is that this will accelerate at a constant rate, g. Okay, so now how do we bring that into play? Acceleration is which derivative? So we'll say d squared s over dt squared. And since gravity is moving this downward, we'll say that that acceleration would have to be equal to minus g. With the initial conditions, bless you. Initial height, S naught, and initial velocity, y naught. And again, this equation, along with the set of initial conditions, is called an IVP, an initial value problem. Okay, I think we mentioned that earlier, but just to make sure that we got that. Okay, so this is just one scenario. Okay, here's a differential equation that models a free-falling body. Here's a set of initial conditions. That's all it is. Okay? Any questions on that particular problem? So we're missing Brandon and yes.
So we have to write out like a full Phoenix equation. Is that totally?
This is all you need. We just want the differential equation that gives us what's going on. So we don't have to go ahead and solve it or anything yet. Okay. Here's another one. Mass on a spring. So let's say we have a spring attached to something. We then attach a mass to it. This is now what we call the equilibrium position. And let's say that we pull the mass downward. We pull the mass downward, and let's call this distance x of t. So that'll be our variable. Now, I'm not sure in physics what set of assumptions you have, but when we start doing these problems later on, a downward position for us is going to be positive, okay, and upward, so compression will be negative. So if that's a little backwards, I apologize, but that's the way it is in the entire book. So, again, we'll touch on that when we get there, but
Okay, these positive.
no, we're just talking about the position. Yeah. But now, besides that, we have a couple of laws that you guys should remember. What's Hooke's law? Good. And then combine that with, yep,
Oh yeah.
and now we have a differential equation. MA is going to equal negative kx.
What is context? Is K a constant?
K is the spring constant from the stretch, yeah. And x is the amount, the displacement from equilibrium to whatever. So x is what's varying depending on the time. And then simply, since both of these give you force, you set them equal to each other. And then where does the differential equation come in? Yes. So this would be the same as, let's use the correct variables here. So second derivative, position, we used s before. Here we're going to use x. So d squared x over dt squared, that equals minus kx. And, I mean, look, I'll be pretty flexible as far as what your solutions look like on an exam. If you have this, you're good, but later on what we'll probably do is set everything equal to 0 when possible. It'll just be one of the methods that we use to solve. So this is a good format to have it in. And again, sneak preview. A lot of times we like to get rid of this coefficient. So then what we'll do is rewrite it as d squared x over dt squared plus, and we'll bring in this new constant omega squared x. And we just say that omega squared is the same as k over m.
That just looks like more physics.
Why wouldn't we just? Why can't you just write kx over m?
You can. I'm just planting seeds for later because it's gonna make.
Omega is angular velocity.
Why does the omega help you?
It just clarify. It's just.
Is it omega or is it?
It's an omega.
And like, why is it even?
Because as part of the solutions, it'll clean up the answers later on if we have it as a square constant. You're just gonna have to trust me. But again, right now, don't concern yourself with why are you writing it as omega squared. You can write it if you want. You can write it as k over m times x. That's perfectly fine. You could even have left it. Someone stole my notes, but you could have left it as the initial thing that we wrote down. M d squared x over dt squared equals minus kx. Perfectly fine.
Just for our knowledge.
But for your knowledge, this is where we're headed, right? Okay? Here comes some more moans and groans. The units that this source uses is not what you typically use in physics. In physics, you have force, you have mass, you have distance, you have acceleration. What system do you guys use?
SI.
So what?
Newton.
We have newtons.
Newton, kilogram,
Yep.
meter, per second squared.
Yep. Well, for force, we use pounds. Distance would be in feet.
Oh,
Acceleration would then be
feet per second squared.
feet per second squared. And in case you forgot, it's 32. Here it's 9.8, right? And then the unit of mass is a slug.
What?
That's just what it's called.
So it's just gonna be in the period system, not in the metric system.
Okay.
Right. They occasionally bring in metric, but usually it's in this format.
But how is count?
How do they translate over?
PSI.
Well, let's see.
Pound is your weight.
Pound is a weight, right?
Well, yeah, that makes sense.
So mg is weight. And let's say we have something like,
I feel like my actual question is what is this called?
and that's what I was about to show you. So let's pretend, for example, that you have a weight of 8 pounds, a force of 8 pounds. That's going to be mg, right? Now, in this system, what's g?
Feet per second squared.
But what constant?
32.
32, right? Here's a slug. If you divide pounds by feet per second squared, you get what we call a slug. So what would be the equivalent units for a slug?
Pounds squared over feet.
Yes.
Okay. That's just so confusing.
It is. Maybe that's why they decided to just call it a slug. Who knows? Okay? But this is, again, just planting seeds for later. You're not going to be too concerned with this right now. More importantly, you should be able to just model what's going on. So the 2 examples we've done so far hopefully are okay. Yes?
So we're not gonna have to like convert things like that. They'll just give us the values.
Yes. I'm not going to expect you to convert to metric or vice versa. So it's easy. I mean, once you get used to working it, I mean, it's just a different way of solving it. You'll use 32. I mean, if you're a purist and you want to convert to metric, you can certainly do that. It's more work than involved.
I'm gonna
Then
start
you
using
need-
that in physics now.
What's that?
2.2 pounds to a kilogram.
Something like that. Yeah. Okay.
Wait, so what do we need units for in this process? If we're like writing equations, do we need to put units with the equations?
No.
Or-
No. This is a pretty straightforward section. So let's just review another thing here. Newton's law of cooling. Did you guys do that last year?
Yes.
No.
In
But
math.
that was in Science Olympiad.
Oh, okay.
We did that.
That was in technical problem solving last year.
So, think it goes something like this. The rate at which a body cools is proportional to what?
It's the area, temperature, something.
Proportional to the difference in temperature.
Yes. To difference in temperature. And if you're wondering what temperatures, so let's say here we have some sort of cooling body, or cool body, since I ran out of space. And we can say that the temperature at time t models the cooling body's temperature. Okay? Now, outside of that, we have some other temperature. We'll call it T sub m for temperature of the surrounding medium.
Doesn't it cool until they equilibrate in the same temperature?
Mm-hmm. But now, just from Newton's law of cooling, we have a differential equation, right? The rate at which a body cools. So what is that derivative?
D.
d capital T, d little t, that would be your rate of change of temperature with respect to time, right? Is proportional means you got a constant to the proportional to the difference in temperature, so we'll just do T minus surrounding temperature. So this would be Newton's law of cooling, written in a differential equation. What's that?
I feel like it was more complicated last year.
Really?
Yeah.
Oh.
It felt more complicated.
No, like I
But
feel
we
like
had
the statement was longer.
Well, that was the solution for it.
Yeah,
Oh.
We're not solving it yet. So yeah, eventually when we start solving this, yes, you're going to have exponentials and all that good stuff. So that was another example. Here's another one that you guys should be familiar with. Population growth. A very, very simplistic model. We'll clean this one up later when we have more tools under our belt. But a reasonable assumption would be that the more people there are, the more there will be. So working with this assumption, this means that the rate at which the population, let's call it P, expands or grows or whatever, or changes, is proportional to the current population at time t. So what would a differential equation for this scenario be? dp dt, k, what's our dependent? No, it's the same one.
Oh, P and
Right. So again, some of this is working with some previous scenarios that you've dealt with in your math or science upbringing and translating in a differential equation if you haven't done so already. There are several examples in the book. I think you were looking at some of them. There's some pretty pictures that go along with them. I would recommend just kind of looking through those so you can see all the different kinds of applications there are. All I have is one more problem to go through. So this one will be kind of more, I mean, little bit more involved, but not too bad. All right, so let's say we have a tank.
This sounds like a pre-calc problem.
What's wrong with tanks?
But then it asks like how fast the water drains or something.
Oh, we'll get there. And let's say, so yeah, we have some amount of water in there. And let's say at the bottom of the tank there's a circular opening and water is draining or leaving the tank. What's that?
How fast will the fish population increase?
Oh.
And let's see, what else do we have? Let's call A sub B the area of the base. So that would be the area of this circle down here. And let's call A sub O the area of the opening. And let's suppose that the speed or velocity of the water leaving the tank is given by V equals the square root of 2gh.
Oh, I've seen that before somewhere.
Yes. But this is what's given to us. Here's the goal. Find a differential equation that models the height of the water in the tank. So that would be okay. So a good way to approach this, especially if we want a differential equation, which means we need rate of change involved somehow, right? Identify what's changing. So volume's changing. What else? The height. Those are the two variables that change depending on time, right? So let's start with volume. How will the volume change? Well, the volume will decrease, right? What do you guys think? We have enough information. What's that? I heard you guys mumble something and some of it sounded right. What about velocity? Okay, and what else?
Area of the opening.
Area of the opening, right? So that'll get you the right units, right? Velocity times the area, that'll be your volume per second. But yeah, the volume that's changing is just the amount that's coming through. It's almost like we're talking about flux. The amount that's coming through this opening, right? So the area would be A naught. That's your meters squared. The velocity was root 2gh. And that's your meters per second, or whatever standard units you're in. And there's your rate of change in meters cubed per second. Okay, so this is the rate of change for the volume in the tank. Okay, so that's one thing. We still don't have a differential equation that models the height. So what other relationship could we look at? Say that again. I'll write it this way. V equals So just standard area of the base times height is the volume, right? And now since V and H change over time, if we differentiate implicitly, we can start bringing in some derivatives, right? So what would if I differentiate implicitly, what would we get? dV dt, a sub b is fine, that's a constant, dH dt. And now here's where we have our height model. And we know dV dt. So dH dt will be dV dt times 1 over area of the base. So if I clean that up, I'll just write it as minus a naught over, well, a sub 0, I guess it's not a naught, over a sub b times root 2gh. So here's a model for the changing height of the tank. Well, the height of the water in the tank. Yes?
Go over again how dV over or dV equals negative.
Sure. So this is just what? What does that represent? The rate at which volume is changing. And the rate at which volume is changing is basically how much volume of water is leaving the tank, right? So that's meters cubed per second. So one way to look at it is, okay, how could I figure out this volume? Well, I know rate of volume. I know the rate at which the water is leaving, because that's given to us, right? Let's say that's in meters per second. So then the only thing I need now is basically an area. Because if I multiply the area with meters per second, that'll give me the amount of whatever, water, the amount that's leaving per second. Does that make sense? So that's area right here, and then speed gives you a rate of change for volume. Any other questions? Okay, then that's the lesson for today. We're done a little early.